Okay, let's get started. This is lecture 12 of our Computational Microelectronics 2024. So today we will talk about the transient simulation here. Transient means that we wanted to discuss about the time dependent problem. In many cases, if you are working with device simulation, then in many cases your first characterization method is not this time dependent quantity. Let's say that you have a MOSFET here, then what you have to do to characterize this device is first draw certain IV characteristics of course drain current as a function of your gate voltage. Then you will have certain behavior. So if you have sufficiently low gate voltage, then your current would be quite small. And once you have sufficiently high enough gate voltage, then you will have certain drain current which is really meaningful. So once you draw this kind of graph, usually called as input characteristics, then you have to further identify the characteristics same the drain current as a function of now drain voltage. So then of course if you have applied low gate voltage, then there will be no current at all. However, if you apply sufficiently high gate voltage, then first it increase linearly, after that it is reduced, its increase rate is reduced, and eventually it is more and less saturated. So typically people call it as input characteristics of a MOSFET, and this is output characteristics of your MOSFET. It is because this gate terminal is regarded as your input terminal and drain is regarded as your output terminal. But in both cases they share the common factor. This kind of characterization does not consider the speed of your biasing. You assume that you have applied, for example in this case, you have applied a certain drain voltage and certain gate voltage for a while sufficiently long time. After that your drain current will be averaged. So if we just observe in this case our drain current as a function of time, that what we expect from this situation is now we have a certain level of drain current. This level of course is corresponding to this level, so let's call it as I naught, and here I naught. Yes, we will have this form, and we assume that we have waited sufficiently long, so initial phase is now over. After that we just measure this ID drain current for sufficiently long time. Why we have to take this long time average? Otherwise in reality if we just exaggerate its transient form, then the actual ID just looks like this. This is the one actually we have in reality. Even when you have a perfect device, however, when you measure your drain current as a function of time, real time scale, then always its value is fluctuating. So, hmm, so then when you say this one is the right one or this one is the right one, so we cannot say so. So we just consider time averages, time invariant quantity. So simply speaking, we just take DC component of a drain current. So of course, I'm not saying that in the field of device simulation, DC is the only important analysis method. Of course, even in the DC case, time transient behavior is extremely important. However, when we characterize the device, then usually what we do first is just to try to get DC characteristics, input and output characteristics. So in many cases, we assume that our device is just placed at steady state condition. It means that all of time dependencies goes to 0. So we can just solve at instantaneous equations at a certain point. So that was the situation in the device simulation. However, now let's think about the case for process simulation. So of course, even in this process simulation, sometimes we are allowed to just to do this instantaneous solution. However, in many cases, process simulation is related with change of something as a time being. I mean that the shape of your device now, starting from this shape, so if you add something, then you will have another added one. Or for example, initially your borers were just concentrated on this point. However, if you hit this device up, then yes, these dopants will diffuse over your device. So when we consider the initial time, initial condition, and after that, a long time later, if we just measure the dopant profile, then that will show quite much difference. So simply speaking, in the case of process simulation, it would be very difficult to avoid treating the transient behavior. So today we will talk about how can we consider these time dependencies in our simulation. So eventually what we will consider is like this. Here we have position dependency of our physical quantities. So what is the physical quantities in this case? For example, dopant density can be a physical quantity of our interest, and for example, electrostatic potential, that can be also a position dependent quantity, and another one, electron density or density. Also, what we can have is, for example, something like a temperature. Even temperature can be a function of position. At the same time, also it can be a function of time. So both of position dependency and time dependency should be considered in our calculation. So up to now, we are more or less concentrated on this position dependency, and since this 2D or 3D space have certain mesh structures in its discretized form, so we have thought about how can we consider unstructured meshes in 2D or 3D. Today we will talk about how can we consider this time dependency. Now you have basic background for how can you individually consider position dependency and time dependency, but combining them all into a form of a partial differential equation, that is also another topic. So that is beyond today's lecture. But today we will just concentrate on how can you treat the time dependency. Okay. So do you have any question? Then if you have a question, please interrupt me anytime. So okay, now let's go to our okay. Okay, so let's go to this one. Of course, we will later consider more relevant equation in this semester, but today's lecture will be applied to quite a simple circuit, RC circuit. It is not directly related with how can we say our device simulation or process simulation. It was just taken as an example for a certain differential equation considering this time dependency. So now let's think about a series RC circuit. Means that maybe I have prepared its circuit schematic here. Now here we have input voltage, so you can change it. So this is your input, and what you wanted to observe is this node voltage. Yes, between R and C there is a certain node, and this voltage is taken as output, and you wanted to understand the relation between your input and output voltages. So what will happen if I change my amplitude? However, amplitude in this case doesn't play any role because the system itself is a linear system. However, what will happen if I change my frequency? So frequency really makes big differences in this case. So of course, if you are educated in a college level, then you understand what will happen to this system, because especially this capacitance shows its certain behavior as a function of a frequency. However, I'm not saying the analytic way to do that. I wanted to discuss about how can we numerically implement this system into our computer program, then how can we get those solutions. But one thing, before starting our entire lecture today, so I wanted to make a caution to you. So when you perform this kind of analysis, then you will have a very powerful tool to analyze all kinds of this time dependent differential equation. But point is, you must have sufficient knowledge on this problem when it is solvable in an analytic way. So do not just trust our numerical calculation. Oh, I have just learned the simulation code and it gave me this result. Since this is computer generated data, so we must believe it. So this is not a correct way or prepared way to treat our solutions. So always think about certain mistakes you may introduce into your code. So please try to justify your calculation result and try to explain in a plain English. Okay. So anyway, now if we have to solve this system, then we must introduce KCL. Now, since I have already discussed this topic several times in my previous lectures, not in this semester but previous semesters, if you are interested, then please watch our previous video. Simply speaking, this is Kirchhoff's current law, and it just says that the sum of a branch current should be 0. So then what is branch currents? In this case, we can identify two different branch currents. First branch here is this branch, and another branch is now here. This branch is connected to our resistor R, so its current can be easily obtained by the difference between one node and another node divided by its resistance. Then this will be the amount of current in this direction. Direction is important. And also, if we consider this capacitance, this branch will have quite a simple behavior. So time derivative of voltage difference across this capacitor, and this is really grounded. Yes, this is grounded, so it is always regarded as a 0 voltage. In this case, we will have V sub x. So simply speaking, this equation simply says that the sum of resistor branch current and capacitor branch current should vanish. That is KCL we have applied. Then of course we have assumed in this case at time equal 0 we suddenly increase our input voltage to VDD. So means that if we draw time, and let's say that this is a t equal 0, previously we just say that input voltage was 0. Since the input voltage was 0, output voltage was also 0, so every voltage was just 0. However, now we suddenly increase this input voltage. So what we expect is, since this input is excited to VDD, so maybe there will be a certain reaction or response of our system against that excitation. Then what will happen to this one? So that is our expectation. So question is, what is the solution after long time has passed? So if we spend quite a long time and wait for a while, then eventually we must have output voltage equal to the input voltage. Later, then we must have Vx, which is identical to the input voltage. Otherwise, if we have a little difference, if this is not this input case, then a voltage difference occurs between these two nodes of a resistor. It means that we will have certain current conduction. However, if we wait for a long time, then this capacitor doesn't have any contribution to our current. It means that we must have disobeyment of KCL. Resistor wanted to conduct a certain current. However, its balancing part, the capacitor does not allow any current conduction. So it is contradictory. So the only solution we can expect is now Vx should approach to Vin. So that is the situation what we can get. Okay. However, what we wanted to know is not this final solution. What will happen in this case, in this intermediate time steps? So not wait for infinitely long, but so yes, then everybody knows that actually it is given as this analytic solution. This, please note that this is just analytic solution. So your solution, your numerical solution should follow this analytic solution if you did it correctly. So if you have a certain deviation from this analytic solution, it means that you made something wrong or some approximations or errors in this system. So please regard this one as a golden reference. So now it is our next topic. Okay, so here now let me just do a little more about this equation. Here I have some spaces here, so let me just briefly manipulate it. So here we have C and divide left hand side and right side with C, then we can easily eliminate this C here. Then instead we will have RC, yes, and here we have Vx minus V in equal to 0. This is quite straightforward, and when we observe this equation, then Vx, that is regarded as an unknown variable. So we wanted to know this one. And how about V in? In this case, this is regarded as a known variable. So let's just separate it into that way. T plus 1 over RC Vx, that should be balanced by V in divided by RC. So this is the equation we have to solve. In this case, multiplying a certain number to our unknown variable, this term is really easy to implement. If this is your unknown variable, what you have to do is just multiply a number R and C. They are all known quantities, so it is not that difficult. And also, even this right hand term is really easy to evaluate. Why? Because input voltage is given to you and R and C are also known to you, so it is quite easy. The only difficulty to discretize or realize this equation in our computer program is how can you treat this time derivative of our unknown variable. If we have to, for example, if we have to implement this form, then that would not that difficult, because input is known. So since input is known, its derivative can be calculated quite readily. However, the problem comes from this point. The quantity that should be time derivative is not known function but unknown function. So that's the point. So now let's go to the next slide. I think that will give you some clues about difference between two different Euler schemes. Here we have two different schemes to discretize time dependencies. However, they share the same form, Euler. Euler here means that is the name of a famous mathematician. So the reason why we have this Euler is this is the scheme consider only two time instances. So this is the reason why we call it as a Euler scheme. However, please note that there are two different versions of our Euler schemes. So today I would like to introduce the difference between forward Euler and backward Euler schemes. Okay. Following the appearance order of our presentation material, I will just show the Ford-Euler first. In this Ford-Euler scheme, the time derivative is calculated by taking the difference between future and present values. Let's just say that we are now talking about the solution at t sub k. So in this case, if this is a time axis, and let's just say that currently we are at t of k, then certain, for example, let's say that the real solution just looks like this, exponential increase. In this case, if we follow Ford-Euler scheme, then our derivative of this function is calculated by taking the values at this point, present point, and another value t sub k plus 1, the future value, and that is taken, and the finite difference between them, that is used to calculate our time derivative. This sounds really natural. However, please have a look at the opposite one, backward Euler. In this backward Euler, if you wanted to calculate these derivatives, instead of taking the difference between t sub k plus 1 and t sub k, in this backward case, it just takes two values at t sub k and t sub k minus 1, and take this difference to calculate the time derivative. Well, do you have any preference in the implementation, or of course implementation we have preference. However, if we don't consider this numerical implementation, if we just consider some analytic way, then actually if our calculation is correct, if this is correct, then the value calculated from this Ford-Euler method or backward Euler method should be identical. Simply speaking, this backward Euler, this is left limit of our derivative, and this one is just right limit of our derivative. We just take the delta value for positive value for our Ford-Euler, and we just take a negative delta value for our backward Euler. So we have to have the agreement between these two finite differences. So that is what we have to have in reality. However, you know that even in the case of our real space discretization, actually we were not able to make our delta x approach to 0. If everything was perfect, then we have to have infinitely short distance between two different nodes. However, in reality, we have to introduce a finite distance between one node and another node. So at a certain point, we just give up. Okay, this is the resolution we can provide at most. So we will stop here, and we will treat this value is small enough to describe the variation, spatial variation of our physical quantities. Just like this real space treatment, even in the case of this temporal treatment, temporal variation, we just says that although C can show quite rapidly, but our time resolution is just fixed and limited, and yes, that will be small number. So in this case, we have to have any of them. One of them is selected, and that will introduce much difference in our simulation. Okay, so let me just do it together with you, although it is not explicitly known in our case, but why don't we just spend our time to directly apply to our RC problem explicitly. So means that my first trial is okay, I love to apply Ford wheel to this problem. Then I know that previously it was just for example at t equals 0, so Vx that is given as just 0, and now I will consider the very first time step, t equal to delta t, 1 times of delta t. Then what will be v over x? So that will be considered with this linear mode, this Ford Euler method. So let me just do it together with you. So if we follow this way, we must consider v of vx, vt, evaluated what? Evaluated at t equal to 0, not t equal to delta t. So in this case, what is it? This is given by v sub x evaluated at delta t minus vx at 0, divided by delta t. So simply speaking, from its initial condition, we will have vx at delta t divided by delta t. That will be the discretized form of our equation. So then let me just apply it to this equation. Then when t equals 0, then its discretized form of time derivative is simply given as what? Vx over delta t divided by delta t. So are you with me? And how about the second term in the left hand side? Please try to evaluate it from its initial condition. V sub x was actually 0. So 0. And how about this right hand side? Input, yes, now it is given as just 1, so we will, or VDD, so we will have VDD and RC. So simply speaking, by applying this one, then we will have the solution, okay, V sub x at delta t is identical to delta t times VDD RC. Okay, so now you have the solution at 1 times delta t. Then what you can do is, now let's move to t equal to delta t. But please note that actually the reason I explicitly show this procedure is shown here. So by solving this problem, so please once again have a look at this. Here we are now talking about t equal to 0 case, but the solution we get is t the voltage at T equal to delta T. So by evaluating our equation at present case, now we get the solution at future point. So that is done by what? Done by our Ford-Euler scheme. So to you, it sounds quite natural, and why I am talking about this seemingly quite natural thing again and again will be quite clear if you go to the backward Euler case from now on. Now let's go to backward Euler. In this case, our initial time point will be not this t equal to 0. Instead of that, we will consider t equal to delta t. And of course, here we have the same expression. Because in this backward Euler, we have to have delta t and 0 to calculate the time derivative at delta t. So although we have the same expression, so Vx at delta t minus Vx at 0 divided by delta t, but following the backward Euler or following the forward Euler, it is assigned to different time instances. Okay, so now we have different or the same expression because initial condition is the same. Now I will here just to apply our backward Euler to our RC problem. In this case, t equal to now delta t. Then let me just do it. In this case, time derivative just becomes Vx at delta t divided by delta t, as we did previously. And please have a look at this point. The second term is important. Here we have 1 over RC multiplied by Vx. Previously, our evaluation point or present point was just t equal 0. Then now please have a look at what is our time instance. Now it is delta t, and what we have to do is 1 over RC V sub x, and please write down what is it. Here we have to have delta t instead of time 0. So also of course we have VDD RC. This is not changed at all because we have assumed just stepwise excitation. Okay, are you with me? Then now what we can get is from this one. Now here we have V sub x at delta t, and also at the same time we have another dependencies on V sub x at delta t. So simply speaking, we have 1 over delta t plus 1 over RC, and they can be combined together, added together as a coefficient of this quantity, and that is given VDD RC. So what you can get eventually is quite striking here. Now we have V sub x delta t is now given as VDD RC divided by 1 over delta t plus 1 over RC. That is the solution. Point is, please have a look at once again. Previously, when we consider Ford-Euler method, so from the evaluation of our equation at t equals 0, now we get the future value at delta t. And please have a look at now this backward Euler. In this case, we are now evaluating t equal to delta t, that is present value, and what you get is now once again the value at that time instance. So present value and present value, that is the difference. So simply speaking, if you adopt this fourth Euler method, then based upon the present value, you can just push your solutions to fourth. Based upon the solution at t equals 0, then you can just push the solution to t equal delta t. However, in the case of our backward Euler method, in order to get the solution at t equal delta t, we must solve this equation and get the present value. So I don't think that all of you can understand this difference immediately, but please think about their differences again and again. This is quite important. Simply speaking, fourth Euler method can be regarded as just push scheme for our solution variable. However, in the case of backward Euler, it is more involved and actually the solution procedure is required. So maybe it is not that easy to understand at the first glance, but let's just proceed. So now we understand, although they just took one side of this limiting procedure, however, forward and backward Euler show quite different behavior. And what is the preferred scheme for our purpose? Obviously, that is backward Euler one. Why we prefer backward Euler over forward Euler? Because if you take this forward Euler, then this becomes really quite unstable. If you just take this forward one, then as much as your system has some non-linearities, then that will give you quite much troubles in this case. So is our system non-linear or linear? Obviously our system has quite a severe non-linearity, so our preference is always backward Euler. Of course, I'm not saying that in entire computational microelectronics explicitly we always solve backward Euler. There is a certain applications where forward Euler scheme is actually used. So let me just name it. This is Monte Carlo simulation. Monte Carlo simulation of electrons or holes movement based upon Newtonian motion. So in this case, Newtonian means that the Newton's second law, not Newton-Raphson method. Of course, although both names come from one physicist, but I mean that in this case, when we consider movement of electrons in a semi-classical way with random variables, then we call it as Monte Carlo simulation. And in this Monte Carlo simulation, we prefer to use forward Euler scheme because the computational burden is really huge in this Monte Carlo case. So therefore, we prefer to have this kind of approach. However, compared with typical drift diffusion simulation, its portion is quite marginal, so we will consider explicitly only backward Euler scheme. So then now, if we adopt this backward Euler scheme, then of course, as I did, we can do this way. So this is corresponding to the time derivative c times dv over dt, and please note that here we have time steps t sub I and t sub I minus 1. Although we are evaluating this equation at t equal to t sub I, we take the present value and past value, and we assume that, this is important, this present is taken as unknown, and this past value is taken as known value. So in this scheme, past is known and present is unknown. So I wanted to stress once again, it is much different from our treatment in the real space. So think about one-dimensional real space. Yes, this is your X. Then do you have anything like this? Okay, this is a center point, and we know that left point quantity is known, and right, this central quantity is not known. So we will just evaluate equation at center point, and from given left point we just calculate center point. And once the center point is known, then we will move to the right side, and from this right side center point becomes a left one, and we just calculate the derivative in that way and evaluate it and again. So do you have such kind of thing? So actually you don't, just like I did. So usually what you have done in your Laplace equation solution is you solve your equations simultaneously, multiple equations simultaneously. However, in this case, do you solve the equation evaluated at t1, t2, t3 and t100 same time and collect them all 100 times a larger system and solve that system at once to get all kinds of time dependencies? You know that this is not the case. So we have clear difference between spatial treatment and temporal treatment. What we do is space is regarded as a one thing, it's as a one body, and instead time is regarded as something which has a sequential and can be sliced into several pieces. 1 second, 2 seconds, 3 seconds. We can just solve first 1 second, next 1 second, another 1 second, in that way. So time treatment is usually called as time marching. So we don't solve entire time transit at once, but starting from this initial solution, slightly go to next point. You know that this is quite natural because space and time have differences. Time has a clear direction from past to future. However, direction, do you have any preference to positive direction, positive x direction than negative x direction? you don't have any kind of a preference. So that's the reason why. So let me just come back to my first here I just written down this coordinate r comma t, and in this case, although our equations are dependent on the position variable and time variable simultaneously, but our treatment is two-folded. One is for real space, we try to entire system instantaneously, and in the case of a temporal variable, time variable, instead of try to solve them all, we just make slices and step by step manner we try to solve that equation. So please note that the difference between spatial treatment and temporal treatment in computation microelectronics is reference to the most widely used simulation technique. For example, you can raise your hand and ask me a question. Is there any trial to consider all time instances at the same time and get entire system response at the same time once? Yes, there is such kind of attempt. So of course that is quite important for some applications, but compared with the most widely one, relatively small portion in our computational microelectronics, and that's the reason why I just told you that our treatment for spatial variable and temporal variables are different. But if you are interested, then I wanted to ask you search this keyword, harmonic balance. In this technique called as harmonic balance, we even consider variables at different time instances and make a grand system. In this system, not only a solution variable at certain present time instance is considered, but also the entire time instances are treated in an equal base, and by solving that gigantic system, we get the solution at once. Of course, you may feel that that is quite inefficient. Yes, in some sense it is inefficient, but point is, if we consider certain case of a periodic excitation and periodic response, then in some cases harmonic balance can be much more efficient way to calculate systems responses. Okay, but this is not a main topic of our today's talk. Okay, we have spent quite a long time, but I feel that I have delivered the important point already to you. So now in this slide we have made a certain example. Let's just say that every quantity is just have a unit amplitude with proper dimensions. Then you can find that this form. Yes, this is the discretized solution of your RC system when we apply backward Euler scheme, and this is your analytic solution with R equal to C equal to VDD equal to 1. Then well, how can you understand these two equations? So this is analytic solution and this is the golden reference. If our backward Euler solution is deviated from this analytic solution, then that should be regarded as an error. And now you are looking at this one. We just keep R and C, and only the distance between two time points is changes from 1 to smaller numbers. Then let's just run the simulation up to 10 seconds. This 10 seconds is not CPU time, but time in our simulation. So it means that we just consider 10 time points starting from 1 second up to 10 seconds. And exact solution is shown here as blue one, and this one is backward Euler. And you can see that well, the solution, the numerical solution, eventually follow the behavior of a correct solution. Well, it follows VDD. So VDD is given as 1 volt and it follows 1 volt eventually. However, as I told you before, in this case, important quantity is not this final solution, but it's a behavior, intermediate behavior. So it shows a certain difference. Why do we have this visible difference? It is related with our time resolution. Simply speaking, if we have introduced a final resolution, then that error will be reduced. Just like 10 times shorter time distances, so now you have the difference between them. So how do you feel? Well, the first feeling is, okay, the error seems to be quite small than before. However, also at the same time, now you can see that even though we have reduced delta t 10 times, but still there is a small differences. And how about even 10 times smaller differences? Then now we can see that the difference seems to be almost invisible. Well, so that is simple lesson to you. If you wanted to have good enough solution, accurate enough solution, then you must introduce quite a short time difference. Then, unfortunately, that gives you certain problem. So how many points did you use in this case? In this case, you have spent 1,000 time points to get this solution. And how many points did you use? In this case, although the solution is quite bad, but you have used just 10 time points. Well, so you are asked to what is the optimal value of your delta t. So that is a really serious problem. And you know, even in this case, for example, in this case, you need a final resolution. In this case, well, you are okay to have quite a crude approximation. So means that the distance required or optimal distance, time difference is dynamically changing. So if you are building the realistic, practical code competitive to the commercial ones, then your code should have some capabilities to adjust delta t values dynamically. Actually, that algorithm is known to us. So yes, we first of all we can evaluate something and check the change of a previous time matching and expect okay, this will be the good enough distances. But you know, as a rule of thumb, fine time resolution is required to get a good solution. But of course, it always have a trade-off. If you spend too many time points, then immediately it costs you. You must occupy your CPU or GPU longer than before. So if it is not justified as your better analysis, then maybe you are wasting your CPU or GPU times. So that it is understood. And of course, up to now, we have thought about Euler schemes, forward and backward. That too, two time instances and take the finite difference. However, there are other methods, not one method, there are several methods, but I wanted to just one specific one, Gear's second order method. In this case, if we consider, for example, derivative at a certain time instance t sub I, then we take the values at t sub I minus 1. Previously we stopped there, but now in this Gear's second method, now we took even the values at twice previous second nearest past points. So then of course why it is so good, because now think about a shape like this and you wanted to evaluate the time value derivative. If you consider just one time points, for example, you just take this one. However, if you just take two previous values, then you can have these two. Then from this and that, the difference between this and that and difference between this and that can be calculated, and now we feel that its slope is now increasing. So based upon that information, maybe instead of expecting in that way, because our slope is now keep increasing, instead of this just 9 difference, so we can slightly make an adjustment, a little bit steeper one. So therefore now we can have this kind of better method. Okay, however, it has some limitation. Okay, if t equal to ti equal to t2, then we can think about t2, t1, t0. Yes, they are all available. However, at the initial point ti equal to t1, then we are asked to t1, t0 and t minus 1. And do we have a t minus 1? Oh no, we don't. So in this case, we just use a backward Euler scheme. So because backward Euler scheme just requires 2 points, so at the beginning we just take this one. After that, we switched to the Gear's second method, then it gives you a certain value. Point is, well, think about the numerical calculation. Is it more difficult to use Gear's second method than our previous backward Euler method? Actually not, because this is just evaluation, and previously that was regarded as a solution, unknown variable, and even in this Gear's second method, still these two components are just regarded as given numbers, known values. So as much as we remember our trajectories in time axis, then it's okay to use this Gear's second method. So I mean that our cost to switching into this Gear's second method is quite minimal. However, we can get much better result out of this one. Let me just show it. So I have no time to evaluate this equation fully, but this will be the discretized form of our RC circuit, and if we apply it to here, then even when we have delta t equal to 1, then this is the result. And yes, in this case, well, still it's not very successful, but now let's go to delta t equal to 0.1. Do you remember the case for backward Euler? The result was much improved. Yes, we were happy. However, also small difference was remaining. Then please have a look at your result in this same delta t. Can you see the difference between analytic solution and your numerical solution? So you cannot see the difference. So let me just come back to our backward Euler case. Same delta t, and when you go to, yes, this is the result for the same delta t but with backward Euler scheme. You can see some differences. So this is quite convenient to use the second order method. So yes, so simply when we use much final value 0.01, then of course we will have quite a small difference. Already we have a good result with 0.1, so no further visible improvement. Okay, up to now I have just to show the comparison between our numerical solution and analytic solution. And another thing we can do is, now we can define any kind of arbitrary voltage source to our system. You can play with arbitrary voltage source. Instead of this stepwise one, you can also apply sinusoidal one. So please have a look at this one. Then you can get such kind of a solution. So in this case, red and blue doesn't show analytic or numerical solution, but they are just comparing this one. Yes. This one is corresponding to Gears method, and this one is corresponding to the Euler method, and our amplitude shows some difference. Why do we have a smaller amplitude in the case of Euler method? It is because for a given delta t value, it has some tendency to introduce a resistive component into our artificial resistive component into our system. So that's the reason why we have artificially larger damping to our system, so our voltage cannot swing fully according to the analytic solution, but we have a little bit reduced swing due to this artificial component, resistive component inserted due to the Euler method. Okay? So now you can see this result. Okay, so now you have, let's wrap up today's lecture. Today I have explained about time transient. The model system was just a simple RC